So hello everybody, I hope you're doing well. So the announcements for today are that, again, just another reminder that our final exam is on May 4th at 9 a.m. Make sure you don't have any conflicts with that. And it's going to cover all the sections with three exceptions. 1.7, because I told you I wouldn't test on that. 3.8, because we're not going to get to it. And 5.1, because it's the last thing we cover, and I'm just not going to put it on the exam. Just a reminder that homework's due Sunday. And then just before class started, I posted some final exam review materials in Sakai. So there's two things there. There's a practice exam. It doesn't look quite like our exam. I think that exam was designed to be an hour and a half, so you would expect our exam to be a little longer. And then there's a study guide that usually they usually sell every semester. They usually sell a study guide for this class, but this semester they're giving it away for free. So I went ahead and posted that in Sakai. So those are good things to get started if you're thinking about preparing for the final exam. Okay, so other than that, do you guys have any questions before we get started? Okay, well then let's get started. So today we're covering basically the last material that will actually be on the final exam. So this is, I believe, section 4.5. And what it's about is it's something called U substitution. But basically what it is it's a technique that allows us to calculate more antiderivatives than just the ones we've memorized so far. So it's a technique that, and it's related to the chain rule. It's basically the opposite of the chain rule. Like for derivatives, there was chain rule, and for integrals, there's the U substitution that undoes the chain rule. So, if we had been given an integral like this, just looking at this, and from what we know so far, unless you just do a bunch of guessing and checking, then you might not immediately know what this antiderivative is. And so what we're going to talk about today is sort of just kind of a method that lets you identify and simplify integrals that involve a specific pattern. Okay. So yeah, that's the first thing we need to talk about is like what pattern is it that we're trying to identify? And it all really comes from the chain rule. So remember, let me just write down the chain rule for you. So the chain rule said that if I take the derivative of a composite function, so say I have f with g plugged in, so f of g of x, I take the derivative of that, then the chain rule says I should get the derivative of the outside with the inside plugged back in times the derivative of the inside. Okay. And now what we're going to do is we're just going to integrate both sides. So if I put an integral on both sides here, because I can always do the same operation to two sides of an equality and it remains equal because I did the same thing. So I would get something like this. But if you think about it, what happened on the left-hand side? So on the left-hand side, we took a derivative, and then we took an antiderivative, right? This is an indefinite integral, which basically says find the most general antiderivative, right? So if I take a derivative and then an antiderivative, that basically does nothing. Though technically you get a plus c here because you're ending with an antiderivative. So what you would get here is these things basically cancel, and this just gives technically plus c. Okay, so this is basically u substitution here, though it's not going to look exactly like the way we use it, but it shows you the pattern you should be looking for. So the pattern we're going to be looking for is when we're taking an integral, we want to have we want to identify a g of x. Maybe I should do that in yellow. We want to identify a g of x. So we want to find some part of it where the derivative also appears times dx. So we're always looking for these two parts whenever we're trying to do this. And then, what the f prime can be can change pretty drastically. So we're always looking for a function and its derivative times dx. So g and g prime dx. That's kind of the pattern we're looking for. And the way we're going to phrase it is like this. So here's kind of the proper u substitution. Is basically we're going to give these things names. So we're going to substitute in this part is going to be called du. Well, maybe it's probably easier if I say it the other way. So you just choose to call this g of x, which could be something complicated. You just try to call it something simple like u. And then the derivative of u, well, here it's technically the differential. This is sort of a little bit more of a mnemonic than of a rigorous thing. But you can think of if you take u and you take its differential, you get du. So if you remember back, we briefly talked about differentials. All it meant was you take the derivative and then multiply by dx. And so what u substitution says is if you start with something that looks like this, f prime of g of x times the derivative of g dx, then if we set u to be g of x, so we're making a substitution, right? We're just giving things names to simplify things. Then du is going to be the derivative times dx. And it says this integral will then be equal to, well, I replace the g with a u, right? So that was saying if I have a g of x, I can replace it with u, which is here, right? Okay. And then you replace g prime dx, which is here, you replace that with du. So this whole part here just becomes a du, right? So let's get rid of all this. Okay. So yeah, so this is the formula basically, is if you can identify if you have an integral that you're trying to, figure out an antiderivative like this, if you can find a pattern where you can find a g of x and then a g prime of x dx, then you can make this substitution to get a simpler integral, right? And hopefully you can do the simpler integral. Now, it turns out you can go even a little bit further. This also works if you remove the prime here. So you didn't need f to be a derivative already. Oops. So here's kind of the final formula. This is what we're going to be using. So if you can find something with the pattern g and then g prime dx somewhere else, or at the end, you can turn it into a simpler integral. And hopefully the idea is you can do the simpler integral, maybe not the one you started with. Okay. So that would be for indefinite integrals. For definite integrals, so if I start with a definite integral, and it's of that form, you have g of x is sitting inside of some other thing, but then you have its derivative, dx, at the end. Then you can still do the u substitution. But the question is, do the bounds stay the same? So let me just copy down. So here we're going to set u equal to g of x, du equal to g prime of x dx. And if you really sit down and think about it for a while, you'll realize that they have to change, right? Because in the first integral, this is telling you about, you have some complicated function here, and you're trying to find the area between, say, a and b, right? But these are in x's. These are x's. This is the x-axis. Whereas if you go to this other integral, so maybe I should finish my picture. I would be calculating some area here. But if you go to the other integral, now the variable that controls the x-axis isn't x, it's u, right? You're doing this in terms of u. So how are x and u related? Well, they're related exactly by this equation here, right? So when u is a, or I mean when x is a, what is u? So what does the endpoint a translate into in terms of u? Well, it's just, you would plug that into your g, right? Because u is g of x. So that means your starting place, instead of being a, it's really g of a. And your ending is really g of b, right? It's because you did this change of variables, this substitution, that you have to actually change the bounds, because now you're talking about an area under a different function. So this function is going to look different. Who knows what it looks like? It's just f of u. And then so it just turns out that by some miracle of the chain rule, that these bounds are now like this. So it's calculating an area under a different function between different bounds, but somehow these two areas should be the same. That's what we're saying. Okay. Okay, so the moral of the story here was that if you're doing this for definite integrals, and you want to keep your bound, if you want to, well, I'll show you another way of doing it as well. But you somehow have to account for the fact that the bounds have changed. And what you do is you apply your substitution to the bounds. Okay. Okay. So yeah, let's see this in action. Okay, so let's start with some indefinite integrals, and then we'll get to some definite ones in a little bit. So here's the one I started with. And so the strategy, which I kind of said in words, but strategy is to first identify a g of x and g prime of x dx. So you need both of these to appear in your integral. You need the g of x that you chose, and then you need to have the derivative of it times dx to show up. There's a small caveat. This really only needs to work up to a constant. So it can be, so like the g prime of x could be like, you know, you could put a 3 here or a 7 here and it'll still work. You know, you only need to have them be equal up to multiplying by a constant. So maybe I should write to multiplying by a constant. So what, yeah, and then the second step is you just use u sub. So here, really what you're looking for is you're looking for something and then its derivative. And you want to make sure that its derivative is times dx. So I see an x and I see an x squared. And I know the derivative of x squared is 2x. So I might at first think like you might try like u equals x squared. And that'll make you some progress. But it turns out you can do even better here. I'll just tell you the answer for the first one. So let's set u equal to 1 minus x squared. And then du should be minus 2x dx, right? You take the derivative of your u, right? So the derivative of 1 minus x squared was minus 2x. And then you tack on dx. You just always write the dx after it. That's just convention, just to make sure you have all the pieces. Okay, so now we've accounted for this part. So this part will get replaced by u from here, right? But what about the dx? It doesn't look like it matches exactly, right? But what I do see is I see the x dx, that matches with this times this. Okay, so this is the part where I was saying like you only need it up to a constant. So to fix it, you can divide over the minus 2. So x dx, which is what we have in our integral, is the same as du divided by minus 2. Okay, so now if we do this replacement, the thing under the square root just gets replaced by u, and then x dx gets replaced with du over minus 2. So u substitution turned it into this integral. And it's probably easiest if we just pull the minus 1/2 out. And now this is a much easier integral, right? Because square root of u is the same as u to the 1/2. And the antiderivative of u to the 1/2 would be u to the 3/2 divided by 3/2, or times 2/3 plus c. Okay, so you might think you're done now. So we did do an integral now, right? But you have to think about like what was the original problem to do? It was to figure out this integral. And so the antiderivative of a formula that involves x's better also involve x's, right? And so, but my formula only is in terms of u. So maybe I should add a third step here. Third step is go back to x's. Okay, so the way we go back to x's is we just go back and look at, it's getting to be too many colors here. We go and look back at our u. And we just use that. So u is 1 minus x squared, and we just replace it back. We substitute back. Okay, and now that would be our final answer. Okay, so questions about that one? Hopefully you caught a little bit of it. We're going to do a few more, at least a few more. Okay, let's hit another one then. Let's do one with bounds now. Okay, so here's an integral, parentheses. So we have cosine of x and then sine of x, which is rather odd, right? We don't see that very often with a sine function inside of another one. But so when you're doing a definite integral, you still approach it the same way at the beginning. You still look for, what could my g be? Right, so you're looking for a function and then its derivative times dx up to maybe a constant, times a constant. So the thing that jumps out at me is I see a sine of x and then I see a cosine of x. I know those are, one is the derivative of the other, right? And so the one that's times dx is the cosine, right? Because it's on the outside. And when you're choosing your u, you typically want to choose it to be something that's inside of something else, right? Because then when you replace it, it's simpler. So that suggests that you want this part to be u. So you sometimes you just have to try things. Sometimes it's not always obvious which one you should choose, and you have to just pick something, try it, see if it works. If it doesn't work, you try something else. There is a lot of trial and error in integrals. So though, okay, if we did choose sine of x to be u, then du would be its derivative, cosine of x, and then we just tack on dx. That's just always what we do. Okay. And so then if we do the substitution, this integral would change from, so the sine of x will get replaced with u, and then cosine x dx gets replaced with du. So you actually end up with this fairly simple integral. But we didn't account for the bounds now. So what do we do about the bounds? Well, what we do is we always just plug them into our u. That's sort of the most straightforward way. So our bounds would be, so u of pi over 2 would be sine of pi over 2, which is 1. So this one just becomes a 1. And then the bottom bound would be u of 0 is sine of 0, which is 0. So you'd be left with this new but simpler integral. And now we can actually do this integral. So we actually haven't done the integral yet, right? We just did a substitution to make it simpler. And so yeah, what's the antiderivative of sine? That would be a minus cosine. Here we're using the fundamental theorem of calculus again. So we take the antiderivative and we plug in our bounds. And so what would that be? Be minus cosine of 1 minus negative cosine of 0. So what do you get? You get 1 minus cosine of 1. Cosine of 1 is not a nice number. It's some irrational number. Okay. So questions about that one? Okay, let's try another one, and I'll show you. Well, maybe I'll hold off a little bit on that. Let's just crank through a few more of these so you can sort of get the hang of them. Okay, so here's another one. So this one you probably could guess the antiderivative, right? I mean, I've given you things like this before, and you've been able to guess the antiderivative. But let's see if we can do it using U substitution. And so the idea in this one is, well, the thing I want to replace is the inside of the sine, right? Because I only know what the derivative of sine is, sine of t. And if I was to choose U to be just pi times t, then du would be the derivative of that, which is just pi. And then we always just tack on, the derivative of whatever is here, right? So if you're taking a t derivative, you tack on dt. And so in my integral, I only have dt, right? I don't have the pi times dt. So that means I want to solve for dt, which will end up being du over pi. So dt will get replaced with this. Whereas pi t will get replaced with u. And so in the end, you'll end up with a sine of u times du over pi, or probably a better way to write this, if you think about it, is this, but now we lost our bounds, right? So we have to make sure that we account for the bounds here. Okay, and so to do that, we always just plug the bounds into our u. So u at 0 is pi times 0, which is 0, and u at a half is pi times a half, so pi over 2. So this changes the integral to be 0 to pi over 2. Okay, and now this is an integral we can do, right? We know the antiderivative of sine of u. That'll be just negative cosine of u. And we have to evaluate from 0 to pi over 2 by the fundamental theorem. Toss everything in, so it'll be minus a half cosine of pi over 2, that's just 0, minus negative a half cosine of 0. Work all that out. The first term is just 0 plus a half times 1, so you just get a half. Okay. Let's see, where are we on time? Okay, let's do one more and then we'll talk about something else for a little bit. So let's actually just go through two of these, see if we can do them a little quicker. This is something where you just have to see a lot of examples and sort of get the hang of choosing the g and the g prime. Well, you're really only choosing g and making sure that g prime is there. So here I have cosine cubed of theta times sine of theta d theta from 0 to pi. And then we'll do another one. Maybe we'll do which one should we do? This one maybe. Okay, but let's look at the first one. So I'm trying to find a function, g, and typically g is something that lives like inside of another function, because it's sort of undoing the chain rule. And then I want to make sure I choose something, and then I also see that thing times derivative, times d theta. And so, I mean, there's kind of two obvious options here that you could either choose u to be sine or to be cosine. And if you think about it, cosine cubed is really the kind of the same as, or I mean, it's exactly the same as writing it like this, right? But if you write it like this, it's very clear that like this would be a better thing to choose to be u, because then the integral will be very simple. And so if I try u to be cosine, then I do see its derivative sine showing up. Though it's off by a minus, but that's okay because a minus is a constant. So let's try cosine of u, or cosine of theta. Then our du has to be the derivative of cosine minus sine, and then we just tack on d theta, right? And now we try to match things up. So the cosine theta here will get replaced with the u. And then I see a sine theta d theta. So that's only here, right? So there's this extra negative. So to fix it, what we should do is we should solve for the part we have. You know, you could think of this as dividing by -1, or an easier way to write it is just minus du. And so the sine theta d theta will get replaced with minus du. Okay, so if we do that, what happens? It'll be the integral of just u cubed now, and then I'll have a minus du. But an easier way of writing that would just be minus the integral of u cubed du. But then we got to make sure we account for the bounds if there are any. So if we look at the bounds here, 0 and pi. To get the new bounds, well, we have to say what's u of 0. That would be cosine of 0, which is 1. U of pi would be cosine of pi, is -1. So we'd have from 1 to -1. And that might feel a little weird because -1 is smaller than 1. So you could switch the bounds and put another negative and make it positive, but it'll work out regardless of how you do it. This is just perfectly fine. So you could do it like this, but let me show you a slightly different way. So another way would be to forget about the bounds. And then when you think about the fundamental theorem of calculus, like what are you really trying to do? You're trying to find an antiderivative and then plug in the bounds. So one thing you can do is you can just do the indefinite integral and then return to x's and then plug in. So you could also just go to, you know, this as an indefinite integral would be, so I guess this is not strictly equal. But when you do if you're doing it this way, then you have to replace it with, go back to x's. So this would be minus cosine to the minus 1/4 cosine to the 4th of theta, right? Because u was cosine theta. And then you would have to plug in your bounds. So would be minus 1/4 cosine to the 4th of theta evaluated from 0 to pi. And so you would get the same answer either way. One way to do it would be to replace the bounds and go have the bounds go from 1 to minus 1, and then you could plug them in immediately here. Or you can just take the antiderivative, go back to thetas or x's or whatever you're doing, and then plug the bounds in there, the original bounds. Okay, so you should get comfortable with at least one of those methods. But in either case, it should come out to be something like this, which is, what is that? That's minus 1/4 times minus 1 to the 4th minus cosine of 0. So that's what, 1/4 minus 1/4. Does that really end up being 0? I don't remember, but it's fine if it does. That can happen, right? There could be some positive areas and some negative areas that cancel out. Okay, so questions about that one? Okay, so I'll do one more of these. And if there's time at the end, we'll do a few more. So here, like I don't see anything really times dx except for a 1. But this is also something I don't immediately know the antiderivative of. But the thing I would like to get rid of is, if this was just like an x or a u, I could do this. So we can go ahead and just try it and see what happens. So if I try setting u equal to this entire underneath part, well, one thing I would recognize is that the derivative of that is just a constant, right? And so a constant dx is really kind of what we're looking for. And so derivative of u would be 7, and then we tack on our dx. We just always do that. And then we look in our integral, and I say, well, I only have the dx. I don't have the 7, right? So we solve for the part we do have, or at least that's one way of doing it. So dx would be du over 7. And now I can use this to replace things. Okay, so I'll do this the other way this time. So I'm going to first just find the antiderivative. So when we replace it, we would get the cube root of u times du over 7. A simpler way to write that might be like that. And so that antiderivative is 1/7 u to the 4/3 times 3/4, right? Because you have to divide by that. And if you were doing this as an indefinite integral, you'd have a plus c. That's not really going to matter here, but. And if I return to x's, that would be 3/28, 1 plus 7x to the 4/3 plus c. Okay, so I found an antiderivative of cube root of 1 plus 7x. So then all I would have to do is I would have to evaluate that between 0 and 1. So you'd have 3/28 to the between 0 and 1. Let's clean that up. Then you plug in 1 plus 7 to the 4/3 minus times 1 plus 0. So you get some number here. It's not a really pretty number. Well, actually, it isn't too bad, is it? So the cube root of 8 is 2. 2 to the 4th is 16. So what do you get? You get 3 over something like that. Okay, so questions? Avery, so there's two ways to do it. So one way would be to do what you said. So I did it the other way. So the other way to do it using what you said would be to, you would do this replacement. So you would end up with the cube root of u times du over 7. And then, yeah, you would fix the bounds. So then you would do u of 0 equals, that's just a 1 plus 7 times 0. U of 1 would be 1 plus 7 times 1. So yeah, then if you do everything in terms of u's, you'd go from 1 to 8, it looks like. And then you would never have to go back to x's. So what I'm saying is you could do it this way, or you could just find an antiderivative in terms of x and then evaluate the original bounds. Or you can transform the bounds and do everything in terms of u's. Right, so then this one would give you and you'll see that's exactly what we had before. Does that make sense? So there are two ways to do this. I didn't want to get you too confused about, because you should, in the beginning you should stick to one method, but it's worth knowing both. So if we compare that up to here, it's very similar. These are the same. Okay, so let's, we have one other little piece of this chapter to talk about. That's not too bad. We're going to go back and talk about symmetry a little bit. So, and really the only types of symmetry we talk about in this class are even and odd, and we're going to talk about how they interact with integrals. All right, so there's some, when areas are symmetric, we can somehow simplify things. And so, so let's think about our two types of symmetries are even functions and odd functions. Those are, and a lot of functions are neither, but some are even, some are odd, and some are neither. And so an even function basically means if you have a function that does something to the right of the x-axis, then it's got to do kind of the reflected thing to the left. Right, it's got to do, so it's got to be like if you fold it in half, it should match. Right, so, and the formula that says that is that f of minus x, if you plug in minus x, it's the same as just plugging in x, right? Saying if I plug an x value in here, that should be the same as plugging minus x in here. These two values should be the same if my picture was perfect. For an odd function, on the other hand, I would say, if the function does something on the right-hand side, well, if I would, whoops, that's not a good picture. And if you were to reflect it across the x-axis, that would be the even part. But if you reflect it against so if you reflect it across y and then across x, you'll get the odd function. So instead of doing exactly the same thing on the other side, it does the negative of it. So basically, if you fold it over the y-axis and then over the x-axis, you end up with the odd function. And so these are the two types of symmetry, right? So this would be an example of an odd function. And the formula that kind of defines an odd function is if you plug in minus x, you get minus what you would get by plugging in positive x. So the idea there is if you choose some x here, and if you take the negative x on the same side, if you were to just reflect it over, you get here, but then if you reflect it to be negative, you get over here, right? Oh, that doesn't look nice. Okay, so is everybody somewhat comfortable with even and odd? Because that's what we're going to be talking about here. Okay. So now, what do these have to do with integrals? Well, nothing by themselves, but if we take certain types of integrals, okay, so to tell you about this, we need a definition. So an interval, so now we're just talking about the number line. So an interval is called, so we're going to just call it symmetric if it is of the form minus c to c for some constant, some number c. So the interval -5 to 5 is symmetric. But if I took something like 0 to 5, this is not symmetric. So this is different than the even odd. This is just for number line stuff, for intervals on the number line. And the idea is, why do we call it symmetrical? Well, if we think about 0 as being the middle, then a symmetrical interval just goes to equal lengths on either side. Right? It's sort of symmetric about 0, right? So we're saying like this distance is the same distance as this. And that's why we call it symmetric. It's just a terminology that helps us kind of keep the core concept. Okay, so an interval is called symmetric if it's just from one number to the negative version, or from the negative of the number to the number itself. Okay. Okay, so how might we use this? So if I was to look at an example like this is something we could do. This is something we could just crank out pretty easily, but it's still a good illustration of what's going on. So what does x cubed look like? X cubed looks something like this. Okay, so what area are we calculating? So let's say 3 is here somewhere, -3 is somewhere here. Then we'll be calculating this area, right? Because we always take the area between the function and the horizontal axis. So we'd be calculating these two areas. Now my picture doesn't look quite symmetrical. Maybe if we move it out a tiny bit more. So based on this picture, what do you guys think the answer to this integral is? What should this be? Any guesses? Yeah, good, it's 0, right? Because basically this area, this area here gets canceled out by this area here because it's the same, but it's the negative of each other, right? These two regions have the same area, but one's counted as negative because it's below the x-axis, and one's counted as positive. So yeah, this is 0. And x cubed was an odd function, and this was a symmetric interval. And so this is exactly what happens all the time when you take the integral of an odd function over a symmetric interval. So this is something that can save you a lot of work if you realize it from the beginning. So sorry, this is sort of just like I guess it's a theorem even. The integral of an odd function over a symmetric interval so I'll even just write it out from -c to c is always 0. And so this can be useful because there's quite often things where we don't know how to take the antiderivative. So if I gave you something like we don't know what the antiderivative of tangent is, but if you think about tangent, if you either use the formula or you think about the graph, tangent looks something like this. So it's an odd function. And so we have an odd function, and then we have the bounds are from minus the number to the number at the positive version of that number. So this is the integral of an odd function over a symmetric interval. This is just automatically 0. We don't even have to know what the antiderivative is. Okay, so sometimes it can save you a lot of work if you just recognize this. I mean, it doesn't happen a whole lot, but it does, in certain situations, it does happen. It can be useful. So the other version of this is what happens if the function's even? So the even one isn't quite as useful. It can still save you some work though. If I take the derivative or the integral, you know, this isn't an example where it saves you much work, but it's easy to understand at least. So if I take the integral of cosine of x from minus pi over 2 to pi over 2, well, cosine of x, you know, if you think about its graph, does something like this. You know, so the point here is cosine is even, right? Cosine is even, sine is odd. Let's try to make it a little more symmetrical. And so pi over 2, minus pi over 2 is over here. Pi over 2 is over here. And if I think about this in terms of two areas, if this was a perfect drawing, there's this area on the right-hand side, and then there's this area on the left-hand side. And these would be the same areas, right? Because it's supposed to be symmetrical. So one thing you can do that sometimes saves you a bit of work, only sometimes, but is if I just integrate from pi over 2, or from 0 to pi over 2, you know, that would be just this area. And so to get the whole area, it's just double that. Okay. And the reason this can save you a little work is a lot of times plugging in 0 is a lot simpler than plugging in other numbers. But yeah, this one doesn't get used quite as much. And so yeah, the theorem that goes along with this one is the integral of an even function over a symmetric interval from minus some number to the positive version is, so I guess we have to give these names. An even function f over a symmetric interval is, you know, so if you start out with this, then what you end up with is you can just take twice the half of it from 0 to c. Okay. So that one probably won't come up quite as often, but still sometimes useful. Okay, so questions about this so far? We're going to probably do one or two more examples and then call it a day. Okay, let's hit some of these examples. Okay, so this integral So really now we only have three techniques for doing integrals. We have, just simplify and take antiderivatives using the most basic formulas, or we have u substitution, or we have maybe the functions odd or even over a symmetric interval. And really only the odd one really helps in that case. And so if you look at this, well, this isn't a basic thing that I can simplify down to the basic formulas and take an antiderivative. So maybe I could try u substitution. But if after you try a couple of them, you'll realize that, there isn't really a good u substitution here, right? Because your u substitution would want to involve having you'd want to have u involving x cubed, probably even just this. And then your du would have a 3x squared. But 3x squared doesn't show up times dx, right? And there's no way to get it in there without introducing extra stuff you can't get rid of. So there's really no way to do this using u substitution either. So then this is, of course, is an example of what we were just talking about. This function, this integrand, is it even or odd? And so remember, if you're not sure, one way you can check is you plug in minus x and see what happens when you simplify. Okay, and if you look at that, if you pull out a negative sign from the bottom, we see that if I plug in minus x, I end up with minus the original. So this means it was odd. Okay, so then I have an odd function. Do I have a symmetric interval? I do. Minus 5 to 5 is symmetric. And so this thing, I don't have to do any calculations now. I know it's just 0 by our theorem, right? Because the area on one side will cancel out the area on the other side. Okay. Though really, this function actually has more problems that we should worry about because it has an asymptote at 0. But we're going to ignore that. Let's see. Let's maybe try one more example. Just try this one. So why don't you guys take a couple minutes and try to do this one. I'll give you a hint. It's u substitution. And then I'll go through it, and then we'll call it a day. So give it a try. Okay. So in this one, I mean, the thing that jumps out immediately when I look at this is, you know, this is an integral involving a secant squared. So I know what the antiderivative of secant squared is, but I don't know what the antiderivative of secant squared of root t is. So it would be ideal to replace this with a u. So maybe we can try and see if that works. What happens if we just try? Sometimes you just have to try these things and see if they work out until you get the hang of recognizing. I mean, the other thing you could recognize is what's the derivative of root t? And that's 1 over 2 root t. And so like this over here will be like related to our g prime. But yeah, if I try u equals square root of t, the derivative of root t is 1 over 2 square roots of t. And I tack on my dt. Now the part I have in my integral here is not this whole thing. I only have dt over root t. So what I'm going to do is I'm going to put the 2 on the other side. Okay, so then if I do this substitution, I end up with secant squared of u, and then this dt over root t gets replaced with 2u. Okay, so I have 2 integral of secant squared of u du. The antiderivative of secant squared is just tangent. And then I tack on plus c because it's an indefinite integral, right? Meaning we want all possible antiderivatives. And I'm done, right? Well, no, not quite. So remember, whenever you're doing one of these indefinite integrals that doesn't have bounds, you have to return to the original variables. So you have to make sure you go back to t's. So remember, u was root t, so this is the same as we plug root t in for u. And this would be our final answer. Alrighty. So any questions about that or anything we talked about today? If not, have a good day and I'll see you on Monday. And just a reminder, I did post sort of the exam review stuff. So take a look at that. Yeah.